Okay, so in the last section, we met the laws of thermodynamics, and it was a little bit maybe abstract, a little bit conceptual. So in this section, I want to give you a concrete example of how we can use these laws of thermodynamics to understand engines, which are devices that use the flow of heat to do work. Okay, so let me start out here with section 9.2.1 of the lecture notes, which is work, heat, and temperature, in a piston. So remember that the first law of thermodynamics says that heat is a type of energy, and that means that we can alter the internal energy of a system not only by doing mechanical work on it, but also by allowing heat to flow into or out of the system somehow. So let's start out by considering like a cartoon of a piston. Right, so piston, I've got some like cylinder, it's filled up with some gas. And I want to know, how could I increase the temperature of the gas inside the piston, right? Increasing the internal kinetic energy of the gas. Of course, the most obvious answer is that, well, I could light a fire over here, right? I could light a fire right here and heat up the piston, and then heat would flow from, this burning chemical reaction. It would come into contact with, the heat would flow into the piston itself, and the piston would transfer thermal energy to the gas molecules, right? So that's one way of increasing the temperature of the gas. But another way to increase the temperature of the gas is to do mechanical work, right? So for instance, I could go from here to, push this piston down quite rapidly. And now this is another way. Also do mechanical work. If you like, you can think of this like at the level of the particles, the atoms and molecules in the gas itself. And this piston, when we push it down rapidly, that's almost like thwapping all of the molecules in the gas with like a giant tennis racket, right? Imparting extra momentum to those particles, and in that way increasing the temperature, right? Now, importantly, the process can also go either way. We can do work on the piston, right, to compress the chamber of gas, and that kind of puts energy into the system, or we can let the gas do work against the piston. So for instance, if we have this like higher pressure, higher temperature gas, I can say, well, let's unlock this piston and let the gas molecules push the piston back out, right? Letting the gas expand, doing work back against the piston, right? Again, the way that all of these concepts are linked is by the first law, right? So remember, the first law says that the change in internal energy, say of the gas in this piston, is given by, well, how much heat is flowing into the gas and how much work is the gas doing on its environment. And again, remember this sign convention where if the gas does positive work against the piston to move the piston up, then the gas is losing some of its internal energy. If we are doing positive work on the gas, that means the gas is doing negative work on us. So us doing work on the piston is like increasing the kinetic energy, increasing the internal kinetic energy of this gas, right? Now, not only can this process go either way, right? Like heat can flow into the gas, heat can flow out of the gas, we can do work on the gas can do work back on the piston. Actually, the consequences and the way that each of these processes unfold can sometimes be a little bit subtle. So as an example, suppose I ask, when you do work to compress the gas, in the piston, does the temperature of the gas go up? Does it go down? Does it stay the same? What happens to the temperature of the gas? From the discussion we just had, you might think that the answer is, well, I do work, that's like the giant tennis racket thwapping all the molecules. When I do work on the gas, the temperature of the gas goes up. Actually, it's not always the case, and it depends on how we are compressing the gas. So let me break this down into two cases. Case one is if you compress the gas very quickly. So if you compress very quickly, the gas very quickly, there's no time for any of the mechanisms of natural heat transfer to operate. And so temperature can't easily flow from the gas back out of the system. There's no time for heat to flow. which means this Q that we write, the heat flow in the first law, is basically 0. Okay, and in that case, we can just see, well, if we are doing work and Q is 0, then the internal energy of the gas is definitely changing. Okay, so temperature increases. Okay, now there's a name for these kinds of processes where you're doing something in a way that no heat gets exchanged, and that's called an adiabatic process. Adiabatic process is the name for processes with no heat transferring, no heat transfer. That's if you compress very quickly. Now, on the other hand, what happens, case 2, if you compress very slowly? Compress very, very slowly. Well, in this case, there's plenty of time for any excess thermal energy above the gas's original temperature to flow out of the gas into the piston and then into the surroundings, right? So in this case, heat actually flows out of the gas. So heat, Q is less than 0, heat flows out of the gas. And if you're doing it very slowly, it's doing it in such a way that it's exactly matching the work that you're doing on the gas. So with the absolute value of the heat leaving the gas being the same as the absolute value of the work that you're doing on the gas, okay? So in this case, actually, if we look back up at this equation, right? So if we're doing positive work, which means the gas is doing negative work, but heat is also leaving the gas, so we have minus Q minus some number. That number, these magnitudes balance each other, and that means that actually the internal energy of the gas does not change, right? And that means also that the pressure doesn't change. Okay. The name for these kinds of processes are isothermal processes. Isothermal. An isothermal process, iso meaning the same and thermal meaning thermal, are processes like this, ones in which the temperature is constant, T is constant. And of course, you can have cases in between these things, right? One is the limit where you're doing things so quickly that heat has no time to flow. The other is when you're doing things so slowly that heat can flow to perfectly balance the amount of work you're putting in. And then in between is everything in between. And if you like, these kind of idealized versions of a process that you might put a system through, adiabatic or isothermal, they're kind of like the idealizations that go into, thinking about frictionless systems when we were talking about Newton's laws of motion, right? It's almost never the case that you have a truly frictionless scenario, but sometimes the amount of friction is so small that you can effectively analyze things as if you can ignore friction. And so it's often the case that even though, in the real world, you can't have perfectly isothermal processes or perfectly adiabatic processes, even in the real world, you can pretty well approximate a lot of things by one of these two cases. Okay, and that's what we'll stick to when we're thinking about this. Okay, so this is kind of the initial way that we're using the first law of thermodynamics to think about the balance between, when are we doing work on, say, the gas in a piston, how does heat flow in and out of a piston, and how does that relate to the temperature of the gas inside. Okay, I want to use those ideas to start talking about an engine. Okay, and first let's just briefly sketch out in section 9.2.2 the idea of a very abstract engine, abstract engines. Okay, so schematically, this is what an engine looks like in my brain. So on the one hand, there's a hot place. There's some source of heat. So I could call this a hot place, I could call this a heat source, something like that. Okay, this heat source is going to be connected to an engine, which is some sort of device. Okay, the engine is also going to be connected to a colder place. Cold place. And this is sometimes also called a cold sink because it's a sink where you can dump heat. Cold sink. Okay. The hot place, this heat source, is going to be at some temperature. I'll call that T hot. This cold place is going to be at some other temperature. I'll call that T cold. An engine is a device which lets some amount of heat flow from the heat source to the engine. So Q hot flows from hot to engine. The engine dumps some other amount of heat into a cold sink. So the engine transfers QC from itself to the cold sink. And in the process, it does a certain amount of work. It outputs a certain amount of work. This is schematically what we mean by an engine. It's a device which operates in between things that are at two different temperatures. It takes some amount of heat from the heat source, it does some work with it, and it dumps some energy into the cold sink. Okay. Engines are often characterized by their efficiency. And the efficiency of an engine, which I'll use this Greek letter eta, just like I used eta for the viscosity in this class. It's a sad fact that we have to reuse a lot of these letters, but so it is. The efficiency of an engine is characterized by, well, how much work are you able to get out of however much heat you're drawing from the hot source, right? Now, by the conservation of energy, right, we know we've got a certain amount of thermal energy going from hot to engine, and then the engine does some amount of work and releases some other amount of thermal energy. So the total amount of work that the engine is able to do, I can also write as, work being equal to the difference between how much heat it takes from the heat source versus how much heat it has to dump into the cold sink. So I can write this as Q hot minus QC, Q hot minus Q cold, divided by Q hot. And this efficiency is always some number that's less than 1. Right? Now, the efficiency can't be bigger than 1 because that would violate the conservation of energy. Heat is a type of energy, work is a type of energy, all of this energy has to go somewhere, and so if the efficiency was greater than 1, we would have been spontaneously creating energy. That's no good. The efficiency also can't equal 1 either, because that would violate Kelvin's statement of the second law. If the efficiency was equal to 1, then that would mean QC would have to be 0, right? And a process with QC being equal to 0 would be one in which you have a certain amount of heat, and then you output all of that heat as work. That would be a process whose only result is the complete conversion of heat to work, and Kelvin's statement of the second law of thermodynamics says that can't happen. So the efficiency can't be bigger than 1, it can't be equal to 1 either. It's possible to have an efficiency equal to 0, and that's the case where you just let heat flow from hotter to colder and you do no work whatsoever. I'm not sure you would call that an engine, but you could set up something like that. Now, what sets the limit? What sets the limit on efficiency? What sets the limit on efficiency for any engine? It turns out the maximum efficiency of any engine, like no matter how clever you are with your engineering, no matter what tricks you do, the maximum efficiency turns out to be related to the two temperatures that you are running your engine between. So just like the efficiency is Q hot minus QC over QH, the maximum efficiency turns out to be T hot minus T cold divided by TH. Right? And this is a result due to a French scientist named Sadi Carnot. Okay. That's quite interesting. In a way, this also helps connect, Kelvin's statement of the second law of thermodynamics, the fact that you can't have an efficiency equal to 1, with the third law of thermodynamics, which tells you you can't really be operating between a heat sink at some temperature and a cold sink, a heat source and a cold sink, where the cold sink is actually at absolute 0, right? If you were at absolute 0, then this efficiency would just be T hot over T hot, that would be 1. But we know from the third law that you can never get to absolute 0. And so in this way too, we see that the efficiency has to be strictly less than 1. All right, this is a kind of schematic of what any engine is basically doing in a thermodynamic sense. It's moving heat, and in the process, it's doing work. So let's actually think about an actual engine. That was an abstract engine. Let's think about an engine made out of an actual gas and piston system. And just so that we have some equations that we can occasionally work with to help us understand what's going on, I'm going to pretend that this is a bunch of ideal gas inside a piston. Okay? And that's just going to help us make things concrete, but a real gas engine will work the same way. So since I'm using the substance that the engine is running on as an ideal gas inside of a piston, let me remind you that the ideal gas law, I'm going to write as the pressure times the volume is equal to this Boltzmann's constant times the number of particles in the gas times the temperature. Okay, so I'm going to put some of this ideal gas inside a piston, and we're going to think about how we can manipulate an ideal gas by running it through a cycle. So we'll run an ideal gas piston through a pressure volume cycle. Okay, so what do I mean when I say that? Let me draw a diagram where on the x-axis, I'm going to draw the volume of the piston, right? So, having a volume over here, a small volume, that means maybe, the piston is mostly compressed down like this. And having a volume up here, that's like the volume has been allowed to expand quite a lot. I'm trying to draw these the same width. I'm bad at drawing. You get the idea. This piston is going up and down. When it goes up, the volume of the ideal gas inside the piston is bigger. And when I'm down here, the volume is getting smaller. So that's going to be the x-axis. And on the y-axis, I'm going to draw the pressure, right? And so, again, every point that I'm going to draw here corresponds to the piston having some volume and the gas inside the piston being at some particular pressure, right? So when I say I'm going to drive this thing through a pressure-volume cycle, what I mean is that I'm going to manipulate the piston in ways that I'll describe in just a second so that it moves around in a repeatable cycle in this pressure-volume space. So I'm going to start it out, for instance, down here. I'm going to do something, and I'm going to describe all these steps in detail to make the pressure go up. Then I'm going to do something to make the volume bigger. So this is going to be leg A of the cycle, leg B of the cycle. I'm going to do something after I've increased the volume. I'm going to do something to reduce the pressure. This is going to be leg C. And then finally, I'm going to do something to bring myself back where I started, simultaneously reducing the pressure and reducing the volume. Okay, so we've drawn this cycle that we're putting the piston through and the ideal gas inside the piston. And this looks like a loop in pressure volume space. And as an engine, you would just be continuously operating this cycle. So we've labeled these different legs of the journey. Let's think about what each of these 4 different segments actually correspond to. So in segment A, what are we doing? We are increasing the pressure of the ideal gas, but the volume is staying the same, right? And from the ideal gas law, if the pressure is increasing, the volume is staying the same, we're not changing the number of particles in the gas, we must be increasing the temperature, right? We must be increasing the temperature. T is increasing. Okay. And also, since the volume of the gas is the same, there's no compression or expansion of the gas, no mechanical work is being done, right? W is equal to 0, right? There's been no work, but the temperature has increased. What this means is that heat must have flowed into the piston. Heat flowed into the gas in the piston. In other words, we lit a fire under the piston or exposed it to some hot temperature or something while we used some mechanism to lock the position of the piston. So we locked the piston position and we lit a fire underneath of it. Okay, that's leg A. Temperature increased, no work was done, heat flowed into the gas. Okay, leg B. In leg B, we are keeping the pressure the same and we're letting the volume increase, right? So again, from the ideal gas law, the pressure is staying the same, the volume is increasing, and that means the temperature must still be increasing. So T is increasing. Again, just looking at the ideal gas law, P is now the same, V is increasing, so T must be increasing too. So temperature is increasing, but now the gas is expanding. It's like the gas is pushing against the piston, doing some positive amount of work, right? Gas does work on the piston. Okay, so let's put some of these things together. Since T is increasing, we know that the internal energy of the gas is increasing, right? Gas molecules are moving faster, the gas's internal kinetic energy is increasing, okay? The work is positive, and since delta U delta U, which is equal to Q minus some positive amount of work, since this is also positive, that means that Q is positive too. Okay? So in other words, the piston is doing work while heat is still flowing into the piston. So it's like we still are holding the piston over a fire, but the piston has been unlocked, so the gas can do work expanding against the piston. Okay, segment C, we're just going to reverse the logic that we said in segment A. Right here, we're going to keep the volume the same again, but we're going to decrease the pressure. Okay, so this is just reverse of A. Okay, so the pressure is decreasing while the volume stays constant. Volume constant means, the work is still 0 on this segment, and the fact that the pressure is decreasing while the volume stays the same means that the temperature is decreasing from the ideal gas law. Okay, the internal energy has decreased while no work has been done. Again, remember, delta U is equal to Q minus W. If W is 0, and if delta U went down, then Q went down too. In other words, heat flowed out of the piston, right? Heat flowed out of the piston. In other words, we've locked the position of the piston again, and then exposed it to something cold, like an ice bath, or in the context of a car engine, just the cooler air that's flowing around the engine block, things like this. Okay. And then finally, in segment D, both pressure and volume are decreasing. So from the ideal gas law, the temperature is definitely decreasing too. Right? And now, right, the volume is decreasing, and that's like work is a negative number. Now, instead of the gas expanding and the gas doing work on the piston, it's like now the gas is doing negative work on the piston. So W is a negative number. Since the temperature is decreasing, delta U is less than 0. And since delta U is equal to Q minus W, so minus a negative number is a positive number, that means for delta U to be less than 0, that means Q must be a negative number, also less than 0. And it has to be less than 0 more than W is less than 0, right? In other words, heat is still flowing out of the gas while the gas is simultaneously compressing. So what have we done? Like physically, we've turned the piston to the unlocked position so that the piston can move while still exposing this whole system to something cold. Okay. Now, I want to emphasize, this is just one out of many different cycles I could have drawn. I also could have drawn something that looks, maybe more like this. I could have drawn, something that was really a perfect square. I could have drawn something that kind of followed these ideal gas processes, where you can work out specific shapes of these curves to make some of these legs actually isothermal processes and the other legs actual adiabatic processes. That helps maximize the efficiency. You can draw lots of these different cycles in pressure, volume, space, even for the simple ideal gas system. And all of these different cycles will give you different efficiencies of your engine. Okay. What this has done, though, is just illustrated the general principle. So, let me write the kind of general principle in terms of work, heat, and the internal energy of the gas during this particular cycle, right? So what we have, is, first, let's think about the work. From what we wrote above, on segments A and C, no work is done. Those were where the volume was locked, the piston was locked, and neither the gas did work on the piston nor piston did work on the gas. On segment B, the gas did positive work. And on segment D, the gas did negative work. And of course, we've arranged things, although I haven't computed anything for you, we've arranged this setup so that the amount of positive work done over here is more than the amount of negative work done over here. So throughout this whole cycle, a certain positive amount of work can be extracted from this ideal gas piston. So that's what's happening with the amount of work on each of these 4 legs of the cycle. What about the heat? heat flowed into the piston, heat flowed into piston on segments A and B, and heat flowed out on segments C and D, right? So there was part of this process where heat was flowing into our piston and part of it where heat was flowing out. And again, the amount of heat flowing out of the piston in total is less than the amount of heat flowing into the piston in total. Okay. And finally, the internal energy. Well, it increased on segments A and B, and it decreased on segments C and D, right? And at the end of the cycle, the internal energy of the gas has to be back exactly where it started, right? How do we know that? The ideal gas law tells us that, the internal energy, which for these ideal gases we can measure just with the temperature, the temperature is just PV divided by K times N. So after I start here, I'm at some particular value of pressure and volume. If I go through a whole cycle, I'm at exactly the same values of pressure and volume, which means I'm at exactly the same temperature, which means I'm back at the same point in the internal energy. Okay. Great. So the internal energy does not change after we complete a cycle. The engine took in more heat on segments A and B than it let flow out on segments C and D, and it did, a total amount of work, which was equal to the positive work done on segment B, and then less the work that was negatively done on segment D. Okay. After all of this, what is it that we have? We have, a piston, which is accepting a certain amount of heat, QA plus the amount of heat on segment A plus the amount of heat on segment B. That's when we were holding it over a fire. It's spitting out on different parts of the cycle the heat from segment C and the heat from segment D, right? That's when we had the piston in an ice bath or exposed to cold air. And during that whole cycle, it did a total amount of work, which I'll write as like the work that it did on segment B less the amount of work that it did negatively on segment D. And since this is a negative number, WB plus WD is something that's somewhat less than just this on its own. Okay? And that is the definition of an engine. Right? And so you can see, just by thinking about like a simple gas inside a piston, where what you have to be able to do are like lock the piston at certain times, and then heat and cool the piston at certain times, letting it be exposed to these two different temperature systems. From that, you can construct a device which does work, right? The particular cycle that we drew in this case is a very idealized version of the cycle that was first used in like a steam engine invented in 1712. In that segment, in that steam engine, segments A and B kind of happened at the same time, and segments C and D happened at the same time. It maybe looked a little bit more like this cycle than like this cycle. It kind of it was kind of interesting. And in the lecture notes, I link to a video which kind of goes through, with like a nice animation, what is going on in that early simple steam engine from the perspective of when is heat flowing in and out, when is work being done, that kind of thing. Exactly. And in the lecture notes, you can also just say, see lecture notes. See lecture notes for what I've written as section 9.2.4, which describes like what is the difference in this kind of pressure volume cycle when we're talking not about just like this single piston or this early steam engine, but like a two-stroke internal combustion engine, or the kinds of four-stroke internal combustion engines that you'll find inside your car, this kind of thing. That's great. That's great. So good. So here we've seen an example of an ideal gas implementing an engine. And in the next section, we'll see how to implement not an engine, but a refrigerator or an air conditioner.